with Lesman Instrument Company. Today we have the pleasure of listening to Mike Madzy. He is the application specialist at Honeywell Thermal Solutions. Specialty is with industrial flame monitoring. So Mike's been with Honeywell on and off for about 15 years. He's got a post-college career commenced as an HVAC and refrigeration field technician all the way back to 1991. And he's been a really great help for us with understanding these products and getting familiar with these products. He's a wealth of information on everything flame scanner related. And so Mike, I'm going to release control over to you just to let everybody know here that is listening on the presentation. If you do have a question for Mike, you can go ahead and type it into the questions portion of the GoToWebinar menu. And we will have some time at the end of the presentation to have Mike answer your questions live. If you are listening to a recording of this presentation, you can submit your questions to us via the website, and either myself or Mike can also answer your questions. So having said that, Mike, take it away.
Awesome, thank you, AJ. And my email and my cell phone number are both shown on this first slide. So if you want to do a screenshot and capture that, that's great. I am a resource, as AJ's described. I support our distributors, end users, contractors, integrators with our products. I typically focus on our industrial products, but this session today is a little bit of, I'd say, product agnostic. This is more around understanding what constitutes the decisions that go into selecting a flame monitor, a little bit about technologies that are out there, why certain technologies are chosen over others. And with that, I have been at Honeywell for 15 of the last 16 years, and I'm going to share a slide deck that I built just before I left on vacation last Tuesday. Specifically for this group. So the question, that I pose is more of a question: is why does this burner have this type of flame sensor? This is a question we often ask ourselves when we're trying to refine a replacement product, or maybe a product that's even maybe more reliable or just cheaper sometimes. So just keep in mind that the flame monitor is, most people would consider, combustion folks would consider, it's the first layer of a burner management system. Usually we think of a burner management system as having multiple levels of safety, and the flame monitoring, the presence or the absence of a flame, is in fact the primary layer of a burner management system. So, what is the presence or absence of a flame, and what does it mean? So the flame monitor, the sensor, detector, scanner, viewing head, they all are really the same in the sense of they all serve the same purpose. They provide intelligence to the logic solver or the burner management system, and we'll talk a little bit about what a logic solver and a burner management system look like, because they're not the same on all applications, as most of you probably are aware. The failure to detect the presence of a flame, could result in an explosion. Any fuel that was to leak into a chamber where there was already the presence of a flame could cause that fuel to catch fire. And if there was no room for expansion, this could relocate the system, if you will. And then also a flame detected when no flame is, when you're not expecting a flame detected when no flame should be present in a furnace could also result in an explosion, in the sense that you could have fuel continue to feed into a furnace because the flame monitor is telling the burner management system, hey, everything's fine, we're burning, keep putting fuel in here, but in fact there's no flame present. You keep adding fuel, eventually it'll find a source of ignition, maybe a solenoid valve, maybe a boiler in the other part of the mechanical room, that sort of thing. So just keep in mind the presence and the absence are both just as important. It's important to know if there is not a flame as well as if there is a flame. And so you may constitute, say, wait, is it because of the fuel and the burner design that it has the type of technology that's in place today? Pre-mixed burners are really usually capable of creating a great target zone for sufficient UV radiation for monitoring. So kind of keep that in mind when you look at burners. It's not always the type of fuel that dictates the sensing technology that is best, but also how the fuel is mixed with air in a lot of cases. So, keep in mind that the overall quantity of UV radiation, typically pales to the amount of IR emittance from a flame. Thus you could argue that an infrared sensor could be used for both, gaseous burners, liquid, or even solid fuel burners like coal. And we'll talk a little bit about, why people would choose to use IR and some of the downsides of choosing IR only. Because I will stress that extreme caution should be applied when using visible light and IR flame sensors to a burner management system. As you can imagine, if you had a detector that you couldn't say gave you 100% reliable information, you don't know if you really want to make, burner management decisions based upon that input. So we'll talk a bit about that as well. And so keep in mind that the fuel and oxygen mix in that target zone, this is the viewing zone that the sensor is looking into, may dictate the best means of monitoring. And I'll expand upon that a little bit. If you have a natural gas burner, most people in our industry would say, oh, I'm going to use a UV flame monitor. But if in fact the target zone is very rich, you may find that the only thing that I can see is in a presence of an IR signature. So you would be drawn to lead with a UV because you're thinking it's natural gas, but then when you get there and you're like, man, this burner doesn't mix air and fuel very well. I can't see much UV, and therefore it might drive you to lean towards an IR technology for that burner design. So there's a lot of factors that play into it. By and large, gas flames on a premix burner, to your eyes and my eyes, they would appear blue, but sometimes they burn red or yellow. But usually it's an indication that there's a problem. And usually that problem is associated with improper ratio of mixed O2 and fuel. So typically, if you look inside of a gas furnace and you see anything outside of yellow and blue, maybe blue towards the base, yellow out towards the tips. If you see anything other than that, you kind of almost get drawn to thinking there's a problem. And I'm not going to cover this chart, but I thought this would be great as a share when you're going back and reflecting on this. Kind of the colors, and these colors stand somewhat true when it comes to an organic or carbon-based fuel. A lot of times people will get so caught up in the color of a flame, but if you don't factor in what's burning, you could get sidetracked. So just kind of keep in mind, this is associated with a natural gas or a coal, fuel oil, those types of things. These colors will typically put you in these ranges of temperature. And with that, I'll pause for a moment in case there is a question regarding this. Okay, very good. And installation factors and common considerations, these will also play into the sensor that is chosen. We've talked heavily about the fuel, the specific fuel, and when I refer to that, it's more of the throughput or the BTU input on the application itself. The distance between the UV detector and the flame can also play into that. Some technologies have a very wide field of view, and they tend to want to be placed close up to the flame. Some detectors have a narrower field of view, and they can actually do quite well either close up or even further back. By moving it further back, sometimes you give it a bigger field of view, if you will. And most manufacturers will identify what their field of view is with their products. And then the area of sighting, always important, where you're looking inside this furnace, that sort of thing. Ambient temperature certainly plays a factor. If you have an application that is, say, 70 degrees Celsius all the time, very, very hot, close to 160 degrees, well, you wouldn't necessarily go and put a product in there that wasn't designed for those ambient conditions. So that ambient will often dictate the options that you have when it comes to selecting a product. And then the presence of an unburned fuel, and I'm talking about not in the furnace, but in the environment in which the scanner sits. If the scanner is in an area where there's a possibility that there's a combustible mix airborne, then you probably want to have a sealed detector, something that is classified enclosure, maybe like an IP64, 65, 66, something that's going to give you protection from a spark igniting that airborne fuel, fuel mixture in this case. And then is what's being burned in the furnace, and when I refer to furnace, a furnace could be inside of a boiler, I'm talking about the firing chamber, the presence of any vapors that could strongly absorb UV radiation. And an example of that might be if you're doing refinery work where they're using a lot of plant gases, H2S as a fuel, you may find that the release of those fuels when they combust, there's so much moisture that's released that it tends to cause the UV sensor to lose a strong signal because the UV is being actually absorbed by the moisture inside of the furnace. So different considerations need to be taken into account for that as well. And so I listed a few common sensors just to kind of give you a feel for the different technologies and the ranges in which their sensitivity lies. And I put really the two big brands that I think you probably are familiar with, which is Honeywell and FireEye. Now I'm making quite a bit of assumption there, but I'm just thinking about the line card at Lesman and the background and experiences I've had with the folks at Lesman. So you see these different ranges, and you may wonder, like, well, you know, what does that really mean? And so 185, that is towards the left. If you were to look at a color chart, this would be nearly to the left of it. And as you go to the right, the values get much higher. As you get to the right of the chart, we tend to find where things like an oil flame might reside up around, say, 1,500 nanometers, where our UV is much further to the left. And you would, you know, maybe be drawn to say something with a broader spectrum is probably a better choice. And by and large, you're 100% correct. If you were to find a product with a broader spectrum like this C7076 with this broad spectral range, you might find that to be more reliable than a product that has a narrower band, because the flame may it may move in and out of those ranges. And the closer it stays to the heart of this range, the better the more activity you'll get out of the sensor itself. One of the things you might find as you're doing this type of work, there's a lot of manufacturers that lean towards solid state sensors. And usually solid state sensors, when it comes to the UV solid state, they tend to start with a UV sensitivity north of 200 nanometers, closer to visible light. I really recommend using these products only to solve problems. If you have a very difficult system, very difficult to sense the flame on a system, these can sometimes be problem solvers. The downside is if somebody is doing maintenance when this thing's in an off cycle, a flashlight is like all it's going to take to cause this thing to go into a lockout, meaning it might not be available when it comes out of a standby condition. You think about a boiler that's sitting in standby and somebody opens up the a visual door or some sort of inspection door and allows light into the furnace. There's a possibility if that light is, you know, reflected off of, say, an arc or a spark or a flashlight, it could cause the system, the burner management system that's in place, to say, hey, flame detected when we weren't expecting a flame, we're going to be in a lockout state. Now that could require somebody to physically come out to the site to reset it in order for that burner to cycle back on when the call for heat comes back. So keep that in mind. And I did capture some of the products that I support daily, which these are these S706, 806, and the U2s, and the S5 series products. I only included the UV only models in this little slide, but you can see the spectral range is relatively low and even somewhat tight. The good thing is these sensors, being that they are UV tubes, they will work really well with premix burners, as well as they work exceptionally well with low NOx burners. Low NOx burners tend to have slower, lazier flames, and you want to use a sensor that doesn't require rapid movement of the flame in order to excite the sensor. By and large, when you get to solid state products, they're going to really be looking for faster moving targets. They're flicker based, so these solid state sensors that are on the market are sensors as well, or they fall into the same category. These IR sensors tend to be all flicker based, and then the UV solid state are also flicker based, meaning they have a spectral range of sensitivity, but there's also a component based upon the speed in which that light is moving. And so you need to have both in order to satisfy the sensor and excite them. And if you have a low NOx burner, there's a good chance that the flame will be a bit lazier. That lazier flame will tend not to work so well with those types of sensors. So as you're doing upgrades, modifications, burner replacement, things like that, if you do that type of work and you're going towards low NOx, just be cautious. Maybe add a couple $1,000s on a line item just in case you need to upgrade or enhance the sensing technology as part of that project. It's very common for that. The other thing that can drive, or one of the other things that can drive the selection that you have of products is the NFPA and the ASME safety standards. And some of you may even follow some, you may work for folks or even be part of an API following. API is usually followed by petrochemical and refinery users, but I do see some folks adopting it even at the power generation level and those sorts of things. Most of those are recommended best practice. They don't use the word shall so much as they do provide some guidance. And I'll touch a little bit on what these standards look like. So, but when you're taking a look, this is a very simplistic flow chart, if you will. You could take a look and figure out, do I have a fluid heater? Do I have an oven? Do I have a boiler? And then based on this boiler, is it greater than 12.5 million BTUs, or is it less than? So if it's greater, I'm going to go to NFPA 85. If it's less than, I can look at CSD 1. And I'm going to make assumptions that some of you are in areas where CSD 1 is the law of the land. And that being the case, this might mean a bit to you. Other people, such as folks in Texas, which none of you are probably, Texas doesn't follow CSD 1. So it's not as applicable. So looking at some of these standards, and I won't go too deep into these because I know we've only got like 45 minutes plus some time for some question and answers. But so the standards themselves will call out details about selecting a detector. And one of the things you're going to find in larger applications greater than 12.5 million BTUs, or they run beyond 24 hours in duration, most of the standards are going to drive you to use a self-checking flame monitor or detector, sensor, you name it, scanner. There's a number of different words depending on the standard that you're into, but by and large, if you're going to be running beyond 24 hours or with a copious amount of fuel, like 12.5 million BTUs or more, they recommend that the detectors be, or not even recommend, they require that the detectors be self-checking. Most of the legacy self-checking detectors that are out there, they utilize a shutter technology. That shutter is just what it sounds like. It's actually a mechanical moving component inside the viewing head. It temporarily goes in front of the sensor to blind it from the furnace. And during that period in which the shutter's in front of the detector's sensing element, it provides a temporary false signal so that your burner management can keep functioning, because this is happening every 5 seconds. But behind the curtain, it's comparing the output of that sensor to what it's expecting. When that shutter's in front of that sensor, it's expecting that sensor to put out 0. So if, in fact, that sensor sees a value when the shutter should be closed, it's going to have a diagnostic fault failure. And there's a number of reasons why these fail. 1, the shutter could be broke. 2, you could have a runaway sensor. Now, a UV tube sensor, which majority of the products that I showed you on that earlier UV slide, those all have a UV tube in them. And the UV tube, if it's exposed to UV for a long enough period of time and it's an excessively, I'll call it a very potent UV source, a very bright flame, very close up proximity to the sensor, it could cause that sensor to become oversaturated, and eventually that sensor will start creating an output without a flame present. This is a very dangerous, condition. And so by having that shutter there, we're checking to make sure that that doesn't occur. It doesn't happen very often. I will say that of the thousands of viewing head failures that I've seen, very few of them have failed based upon that condition, but it is a concern, and it's mentioned in both NFPA 85, 86 also brings the same information forward that you need to be using self-checking scanners. They even go a little bit further in 86 and start talking about, hey, in a case where your flame detection can see the spark and it possibly can create a flame signal, you need to exercise what they would call early spark termination, which means that for a period of time during a attempt for trial of ignition, you actually, once you have a flame present, or sometimes it can be based upon a time period. So let's just say for the first 10 seconds of trial, you get the sparker in, you get the pilot valve open. At the end of that 10 seconds, if the flame monitor says, hey, I've got a flame, it continues to hold the pilot valve for possibly up to 5 more seconds. At the same time, it looks to say, hey, do I still have a flame, or was I literally faked out by that spark? And so this standard will call out that you need to take notice of this and realize if you are picking up the spark. The easiest way to do this is to grab that last manual valve on your fuel train. This is the one just before the burner, and this is one of the reasons it's there. This way, all of your inputs and outputs are falsified into thinking fuel can flow. You close that valve and you try to do start. You try to start your system, and then pay attention to the display on your flame monitor. See if there's voltage. See if there's a signal coming back when it's just sparking. If it is, try to manipulate the field of view if that's a possibility. In some cases, I've seen this on some smaller boilers where people have actually had to go in and add some sort of a deflector to prevent the viewing head from being able to see the spark on the ignition tip. So just kind of keep those things in mind, that there is procedures for doing these tests. And if you've ever seen the 7800 checklist, there's an ARM 7800 checklist. One of those tests calls out how to do this direct spark ignition test. NFPA 87, this is a standard that many of you may be unfamiliar with unless you do industrial work. This is for fluid-backed heaters. It was often covered by CSD1 and NFPA 86. People would kind of use the blending of different standards. Well, 87 is now a standard. It's been out, I think, since 2011 as a standard. It started out as a recommended best practice, meaning it didn't have a lot of the use of shall, had a lot of this recommended and should verbiage. But as this standard has evolved, this NFPA 87 recommended best practice, they started to incorporate the word shall. And this covers things like a reboiler, bath heaters, those types of things, where you're not creating steam necessarily, but you're heating up fluid. You're directly firing into a chamber that is, making a direct exchange with a fluid to heat that fluid. That is a very common standard. And then the CSD1, which is the one that probably most of you are either aware of or familiar with, based upon the BTU input of the system. You have a vertical column, and this is a checklist that if you're not familiar with this checklist, that email address that I shared with you earlier, I would shoot me an email saying, hey, I don't have an CSD1 checklist. These are fantastic to print on 11 by 17 cardstock. This is a checklist, and granted, it looks like it's tiny. This is actually a 2-page, it'll create 2 11 by 17s perfect. So I do a double side print one side on the front, all the notes, because there's footnotes, all the footnotes are on the back. This is one of the best ways to keep your technicians organized or your maintenance people organized, because I think we have a blend maybe of end users and contractors on the call. This chart, this template, if you will, is fantastic for keeping an organization to your maintenance visits. If you do an annual for a customer, this is a great template for you. It's even got a spot on the left-hand side to populate with what's installed. You can check it off. You can write notes in here. There's quite a bit more on this sheet on the sides, documenting, you know, the boiler, the location of the boiler, the owner, the insurance, all those kinds of things. But this is a great template to grab from me if you don't have it already. And then here are some of the standards that are reflected upon from American Petroleum API. And so they have a number of different ones of the heat recovery steam generators. They have one for fired heaters, industrial boilers. And the most common one to look at, most people that'll pull me in, they'll be utilizing what they call their recommended practice of 556, which is applying instrumentation to a fired heater. And there's also a new standard coming out called 565, and that is very specific for reaction furnaces, which are a bit of a heat recovery application. So they've been kind of treating them like boilers over the years, but the fuel is so extreme that the standard of NFPA 5 doesn't really fit it. So they're creating a new standard called 565. And we actually have a gentleman by the name of Richard Reyes who sits on that committee to help lobby to get our suggestions in as well. So just kind of keep in mind that these standards are out there and they're relevant to the type of flame detector in the location, how they should be utilized. These are all suggested in this API. API standards are probably the best readings. Most of the standards are terrible to read. They're like reading a dictionary. API standards are a bit like reading a book, where people are talking a bit, not people, but the author is describing applying the product and why you do things. They give you more of a why. It's not so much prescriptive as it is performance-based suggestions. And so here's some more reasons why you might, you know, reflect on the type of sensor you're using. You know, what is the logic solver or flame relay in use? So some of the most common logic solvers used for combustion safety, the one most of us probably know, are the flame safeguard products out there. These are safety controllers that ensure the safe and reliable startup, monitoring, and shutdown of a fired asset. You can look at FireEye, you can look at Honeywell. There's a number of different manufacturers that make these canned solutions or fixed solutions. And then we see programmable logic solvers. These can be, you know, a hybrid system, or they can be a full-blown safety PLC. We see a lot of people using general purpose PLCs, and then they'll put safeguards underneath of them. And the reason they do that is the programmable logic solver gives them more flexibility. A lot of people don't want to get stuck into using relays and switches. They actually want to use transmitters. Well, most of the flame safeguard systems that are out there, they only know a discrete environment. They're not used to working with, you know, analog signals. And so you use the general purpose PLC to take those analogs, give you a lot of intelligence and data, but then they provide a discrete back to the burner management system, the flame safeguard in this case, for a permissive. And I'll give you an example of that. You may put a transmitter for your low and high gas pressure on the fuel train. And in a transmitter, you're looking at a 4 to 20 milliamp signal versus the old school method of, hey, I've got a switch, and then the switch is either open or closed. Well, that doesn't give you a lot of data. And it's actually a little bit dangerous, because you think, well, that a switch could get stuck in a position, could get tack welded, those kinds of things. Where a transmitter, there's always movement, and movement is good because it gives you that comfort that, hey, the transmitter's working, because there's no fuel train that stays rock solid. They all move a little bit. as that regulator is adjusting for throughput changes, demand changes on it, you're going to see slight movements, and you'll see that in a transmitter. And then the third type of logic solver that most people overlook, this is a supervised boiler, the power plant, where they have instruments that give the operators data. They're not necessarily automated. Not every safety aspect of a power gen boiler is automated. A lot of it is up to the operators. So these would really constitute the three types of flame safeguards. But when we look at the flame safeguard, and I'm talking a little bit fast because I know we're really trying to shoehorn this into an hour. And I don't have a whole lot of slides left, but I do have a lot that we could talk about, and I encourage a lot of questions following this. But you know, Flame Safeguard, I'd refer to this as really a plug and play. They're configured for specific functionality, which makes them great because you can replicate things, cookie cutter, if you will. Manufacturers can put the same device on all their products. Distributors can stock those same models. Maybe they have a couple selector switches, maybe they have a couple jumpers, depending on the manufacturer, to allow them to operate for the application, the capacity, and that sort of thing. So we see, UV tube with non-checking. Think of like a C7027 for an example. The UV tube, maybe it's a 2-wire sensor. Then you have self-checking models, which historically have had mechanical shutters, and by and large, that's still the case. There's solid state. We talked about these. These are flicker-based UV, and then there's also solid state infrared, flicker-based as well. And then we have rectification through flame rod. This is by and large considered still the safest approach for flame monitoring. But as most of us know, if you've been around long enough, if you try to depend on a flame rod for a main flame monitoring, you're going to be out there every 12 to 14 months replacing that flame rod. It's not intended for continual use on a main flame. Even on a pilot, you're lucky if you get more than 14 or 15 months if it's a continuous pilot. So,
hey Mike, I've got a question from one of the attendees, Paul. He's asking about the use of Flame Safeguard with a PLC, and he's asking, so can a PLC be used for translating? Can't the PLC be faked out?
Those are great questions, and yes, it could be faked out, because it could be manipulated. Settings can be manipulated, settings can be changed, and that is one of the larger concerns, and that's why so many folks have limited themselves with a PLC to do more of the air side of the system and not as much of the burner management. It is my recommendation that a safety PLC be used, one where the software can be the logic can be isolated with a password. That is a requirement on most of the safety standards for logic that is related to the safety of the system. That should be password protected in the secure section of the logic solver. So yes, it could be faked out, and this is not everybody is doing PLCs with Flame Safeguard, but it does give you a lot of flexibility, and then you can do all, like I say, if it's done properly. And most of the guys that are doing it properly, they like that concept because they say the Flame Safeguard is intended, it's the liability is on FireEye, the liability is on Honeywell for it to do its job properly. It's a lockdown. But if you're intertwined in the permissive, you could argue and say that the PLC has the potential to override this system and take it to an unsafe state. So perhaps with the next slide might shed a little more light on that as well. And I don't know if that totally answered his question, but I'm hoping maybe the next slide will. And it's safe to say that most flame safeguard systems are really only compatible with that brand of sensors. There are some manufacturers that have created hybrid systems, if you will. So they're just looking for rectification. So anybody who's got like a basic rectification sensor could be connected to it. I would exercise caution when using systems of multi-brands, because to me, there always seems like there's a little bit of a liability you might be taking on, because those products are not tested together. They're not, the certification certificates they have rarely include, you know, you're not going to find like a 7800 SIL 3 document that says it's, you know, that's been tested with a FireEye sensor. It's always going to be tested with a Honeywell sensor. FireEye is always going to be tested with a FireEye sensor, and so on. And then within the flame safeguards, they really come in, you could call it 3 variants, but most commonly there's a primary and a programmer. We think of really primaries as falling on, you know, atmospheric applications, and programmers tend to fall more on power burners, or even power boilers at this point in this conversation. But there, you know, you could say there's some other variants, and some of the primaries have some additional functionality that makes you think they're almost capable of being a programmer. But by and large, primary, usually they do not have an output to drive a motor, and they also don't have a set of contacts to allow modulation. Programmers who tend to have an output for motors to drive a fan, combustion air fan, and they'll typically have additional timing functions as part of their logic. So when we get into the PLCs, I mentioned this, there's a couple different variants. So the hybrid, this is the general purpose PLC handling the non-safety checks and some permissives. They're usually integrated with a flame safeguard. Limited design liability. They try to push some of the liability back on the manufacturer of the flame safeguard, and they have the ability to utilize, you know, flame safeguards traditional sensing options. So all those C7012, 7061, 7060, 7961s, all those traditional options are all an option with the hybrid approach. And then there's the safety PLC approach. And there's other approaches. This is what I would say a safety PLC approach is one that NFPA, A85, 86, 87, and the API all will get behind if it's done properly, where you can utilize the safety PLC for both flame safeguard and process functions. It gives expanded flexibility. It opens you up to using anyone's flame switches on the market. You know, Durag, FireEye, Honeywell, you name it, Cohen. There's a bunch of them out there. That's one of the flexibilities of the PLC, because it's looking for only a discrete input. A set of contacts closing is all that's necessary into this PLC. But there is a high design liability. If you're designing a burner management system and doing the logic, you take on the responsibility for all of that function blocker ladder logic that's in that PLC. Some manufacturers will offer PLCs with function blocks that are already like NFPA 85 approved. That's a pretty sexy way to approach PLC burner management, in my opinion. I like that. I like those. I like the function block type of programming more than ladder logic. Ladder logic's really easy for somebody to go in and alter and basically bypass functionality and safety. And then the ability, when you're using a safety PLC, the ability to use anyone's monitor. I think I probably already touched on that pretty well. And when you start thinking about where would safety PLCs be used, because they're very expensive, it usually is larger systems or systems that are very critical, tend to be more challenging to operate, or other subsystems or upstream systems really depend on it. Safety PLCs are going to be found all over refineries, petrochemicals. You'll find these quite a bit on the the tail end of a refinery. So if you're thinking about thermal oxidizers, combustors, incinerators, those types of things, very often you'll find a safety PLC being used as the burner management. And so a supervised system, this is where we're talking about the former Navy boiler operator. He, essentially makes a decision and operational adjustments based on the data from these instruments, the demand requirements, the fuels available, and even weather. And while some of the functions are automated, he may really be the safety system, in fact. And these are typically required to be manned 24/7, 365 days a year. And these are wonderful for me because they typically get outfitted with advanced flame monitors and switches. Some of these are low cost, low complexity. Some of these are advanced because when we get into flame switches, we have the ability to have not only UV or IR, but we can also have models that are UV and IR or UV plus IR, depending on the manufacturer. Some people will separate those signals and provide two outputs, where you could have a UV output and an IR output. Well, where other brands will allow you the ability to add those sensor outputs together and have an aggregate signal to work with. Depending on your application and depending on what you're trying to accomplish, that's typically, an attractive offering when you're taking a risk where you're not really sure, hey, is this going to be UV? Is it going to be IR? Is the fuel going to be consistent, or is it going to be erratic? When you cover your ass by using the UV plus IR model, you kind of built yourself a safety net. You're going to be able to use that product for virtually any fuel. I always tend to lead by trying to sense the flame with the UV technology that's on that product first, and majority of them have an adjustable sensitivity on the UV and the IR. Start out by chasing the signal with the UV, and if you can find sufficient UV, disregard the IR. Don't even turn it on if you don't need to. But if you find that, hey, during certain conditions, certain throughputs, certain fuels that we burn, maybe as an alternate, I find that there's a need for IR during those times. Whether you set up two configurations, one for this fuel, one for an alternate fuel, or you choose to have one setting that you use for all conditions where you have the UV and the IR both working together. These are options with these advanced flame monitoring systems, and these are the types of products that you want to learn a lot more about them. These are the products that I sell and support daily. The multi-burner flame envelope discrimination, this is another key reason to utilize a flame monitor, an advanced flame monitor. Majority of these have adjustable latching points. You can adjust how high this flame signal needs to be in order to latch a relay to say, yes, a flame that meets the criteria has been met. And then you have another value that can be set for, hey, if the flame signal drops below this level, I want this relay to open. And as you can imagine, if you have multiple flames, multiple burners feeding into a furnace, and a power generation would be a good example of this, where you may have, say, up to 40 burners firing into a single furnace area. How do I keep one burner from not thinking it's lit when the other burner across from it or adjacent to it, above or below it, has a flame envelope that's interfering with it? These products can be configured, these industrial flame monitors. They can be adjusted so you can dial out slower moving flames, like flames from another burner that are coming into your field of view on the burner you're intending to sight. They tend to be just the tail ends of the flames. They're moving much slower. You can make adjustments with these products. They have adjustable sensitivity, I mentioned. I also mentioned that they have adjustable latching points, but they also have adjustable filters, and these filters will allow the sensor to be blinded from slower moving flames or even hot refractory. And I think earlier you heard me mention that you got to be really cautious when applying IR technology to applications. And one of those things is IR sensors, by and large, majority of them out there, if you get a surface extremely hot, and when I say extremely hot, I'm 1800 and up, 1750 and up, somewhere in that ballpark. there's a real good chance that the IR sensor is going to get excited by that surface temperature, especially if there's a vibration involved, if there's debris or any kind of material inside the furnace that's being agitated and blown around. It's creating motion and that hot surface. Good chance you're going to develop some sort of an IR signal, and you really want to try to avoid that. And one of the means to doing that on these advanced flame monitors is you can increase the filter setting so that it only sees faster moving flames, and usually you can blind it from this refractory or from those stray flames that are dancing in front of it from an adjacent or opposed burner. The other benefit to these advanced flame monitors is they can usually give you more information than just a flame signal. They can often give you the information from the sensors independently. So how's the IR sensor doing? How's the UV sensor contributing? They can provide a discrete into your burner management system or to your supervised system, depending on what you have. You also get an analog signal, so you can see the intensity, and what is most commonly found beneficial is to take that analog, bring it into somewhat of a historian or a trending machine, a device that they can take in 4 to 20 inputs and trend them over time. So later on, they can do forensics on an event, on an application, or even if they're just trying to fine tune a process. This data can be very valuable. And while they have those discrete and the analogs, there's often Modbus available as well. And over Modbus, you can usually get all the information with exception for analog. Usually you just get numerical values for the outputs of the sensors. In many of the products that are out there, including the ones that I support with Honeywell, you can actually go and program the devices remotely using the Modbus registers as well, eliminating the need for technicians to climb into some precarious locations. If you've ever done work with duct burners, where you have burners that are sometimes 30, 50, 60 feet in the air, they're not that much fun to service on a hot day. You're climbing up a header that's extremely hot. You're getting up there, you're around very hot things. You're on a ladder for no reason, because if you had the Modbus communications, you could talk with those devices, configure the devices, and monitor those devices. Now, you wouldn't do your safety side with Modbus communications, but you can certainly do your forensics with it, and you can do your setup, and even things like you've replaced the flame monitor. The nice thing is you can put the Modbus address in the flame monitor, go install it, and then come back down to the comfort of an air conditioned or heated. You guys are up north. Get into a heated operations room and actually do fine tuning on the flame monitor remotely. Gives you a really nice means for interacting with the devices. And with that, I'm going to open up to questioning. I'm 4 minutes past, but I think we have about 11 minutes for questions.
Okay, we'll hold off on Stuart now. Stuart, you can type in your question into the bottom. We do have another question. What PLC manufacturers offer pre-configured flame safeguard instructions?
So not necessarily instructions, but I know that HMIA, they offer a function block library that's got, it's TUV approved for NFPA 85. And so they'd be one example of a PLC it's not all configured for you, but the logic is locked down in a sense where you need to populate there's a limited amount of information that you need to put on, like a wire sheet, if you will. But they do have function block library that's already TUV approved for NFPA 85. They may have NFPA 86 as well. The last time I was working with them, it was NFPA 85 that they had their function block library approved for. Honeywell has not created such a function block library, but it's definitely one of those on the roadmap. It just hasn't been completed. at this point, it doesn't exist at Honeywell. I imagine there's others that do as well, but HEMA is the one that jumps out at me as being at the forefront of the function block library being dedicated for burner management.
All right, thank you, Mike. And then Stuart typed in this question. He's asking, when is it appropriate to use multiple flame scanners?
Very good question. Yeah, and there's a number of times when that is necessary. One can be where the flame is just in two locations, depending on throughput, where physically the alignment that was provided by the manufacturer of the burner positions you so that, yeah, I can see the flame really good at low fire. When it goes to high fire, I can't see the flame from the the original location. So a lot of times people will go and add a second detector in parallel so that it becomes a 2 out of 2. They'd have to have both scanners go dark before they'll fail. And a lot of people get this kind of inverted, but a 2 out of 2 is a higher reliability than a 1 out of 1. 1 out of 2 is essentially, hey, if either one of the scanners doesn't see a flame, it trips. Most of the time people will do 2 scanners in parallel, meaning they do it 2 out of 2. So if either one of the scanners see it, they're rocking and rolling. The other nice thing is a lot of times is you can take one scanner out, service it, clean the lens, that sort of thing, while the other scanner carries the workload. To say when it can't be used, it's not necessarily I can't think of any application where you can say it can't be used, but you could argue that it should be part of the discussion when they're doing the hazard analysis, the LOPA, the layers of protection analysis, those types of pre-engineering activities, deciding what the burner management system is going to look like, how the logic's going to be structured. Usually at that point, they're meeting with the fire equipment people, finding out, the flame, the geometry of the burner, the vessel itself, the viewing angles that are going to be there. But I find that flames that tend to have a high turn down are ones that typically will fall and end up with 2 scanners on them. Refineries, they're always going to be using 2 out of 2 or 2 out of 3. Majority of the stuff that I do, it's 2 out of 3, meaning 2 of the 3 scanners have to go dark in order for the system to trip. And it's a little safer than a 2 out of 2, theoretically, but that's the most common scenario. And usually these refineries, difficult fuels difficult flames to monitor, really harsh environment where you anticipate on a monitor failing and being replaced on the fly.
Yep, and I was going to make this comment, and Kevin beat me to it as well. But there is also the line burner requirement, where if the line burner is over 3 feet in length, you need to have a second scanner proving flame propagation on the opposite end of the burner from the ignition source, so from that pilot or spark igniter.
That's a good add, and I may have even captured that, but I do remember seeing that verbiage, and I think it might have been 85, but they do if you're monitoring a flame on a duct burner for power generation, the most important is the flame at the far end. The flame close by the introduction point of the gas, it's important, but it's more important, does the flame reach all the way down to the end at the far end?
Absolutely. Is anybody else want to raise their hand or unmute themselves and ask the question to Mike? Okay, I don't see any other activity online, so we're going to end today's webinar. Again, thank you guys for taking the time to come out and join us. I hope you guys got something out of this and found it interesting and helpful in your flame sensing applications. Of course, Mike has his contact information available on the screen, as well as you can contact us at lesman.com as our website. under the trainings portion of the website, we will host a recording as well as the copy of the presentation so that you guys can go through and review that or share that with some colleagues that you think may have interest in learning more about these topics. And you guys have a great Wednesday afternoon, and thank you all for joining us.